Earlier in the course, we saw a numerical method called Euler's method. As a brief reminder, this used the linearization of f at a point x0, y0 given by an initial condition, and the idea was to use a tangent line to generate a point that approximated a point on a solution curve. It was an iterative process, and at that new point on the tangent line, we then found a new slope, created basically a pseudo-tangent line, and found a second point that would approximate another point on the solution curve. And this led to an iterative formula where an x value was a previous x value plus a step size, and a y value was a previous y value plus that step size times a slope. The method was recursive because a new y value depended on a previous y value. Now, because that iterative formula uses approximations, the values that we get this way, the y values, contain what we call local truncation error at every step when we're finding the approximation. I thought I would drop in a warning here. For about the next 6 minutes, we're going to be fairly into the weeds, but I don't want you to think that you need to pay attention to all of it. I want you to start paying attention more when I talk about big OH, you'll see when we get there, and that contrasted with big OH squared. And then after all of that, our work is actually going to begin. Our work in the weeds starts with a reminder of Taylor polynomials. To figure out the maximum size of the error, we actually invoke Taylor polynomials. Suppose a function y of x has k plus 1 derivatives that are continuous on an open interval containing a and x. The kth degree Taylor polynomial with remainder is y of x is equal to y of a plus y prime of a times x minus a, all the way to the kth derivative at a, x minus a to the k divided by k factorial, plus the k plus first derivative of y evaluated at some number c times k minus a to the k plus 1 divided by k plus 1 factorial. I know that was kind of a lot, but from second semester calculus, the kth degree Taylor polynomial was basically all the terms that had an argument of a, and then the remainder is what gave us Taylor's inequality. Generally speaking, the remainder would be the error. In the context of Taylor polynomials and Taylor series, it's because the series is an infinite series. If we add together a finite number of terms, whatever's left is the remainder, and that's the error. We aren't really going to concern ourselves with what c is, but it's some value between x and a. X would be in the interval of convergence, and a would be the center of the series expansion. In the case that k is equal to 1, so we are only looking ever at as high as a first derivative, replacing a using x naught and x using x sub n plus 1, which is x sub n plus h, right? The previous x value plus a step size. We have y of x sub n plus 1 is equal to y of x sub n plus y prime of x sub n times h divided by 1 factorial plus y double prime at c times h squared over 2. And this is exactly the formula for Euler's method plus a remainder term. Now I know that was thick, and there's a lot of text on the screen, but what I want you to get here is that the local truncation error is related to h squared. It's actually y double prime of c times h squared over 2 factorial. C is some value between the previous x value and the new x value. We're not going to try to find a value for c. We're just going to say that the absolute value of the error is mh squared over 2, where m is no smaller than the absolute value of the second derivative of the function over the interval between x sub n and x sub n plus 1. This can kind of bring to mind the way we defined exponential order for a function when we were looking at Laplace transforms. Not to get too much into the details, but we're saying that for Euler's method, an upper bound for the absolute value of the error is mh squared over 2, that being related to y double prime of c times h squared over 2. When we saw exponential order for Laplace transforms, I described it as saying that the function f doesn't grow faster than an exponential, but that means that the function is no bigger than m times some exponential, right? So here we're saying m times h squared over 2 for Euler's method. The vocabulary associated with this is big O h squared. And what that means is that the magnitude of the error depends on h squared. It's not equal to it, but it's related to it. We could say here, for a function of exponential order, it is big O e to the ct, saying essentially there's a bound on the size of f. Okay, we're not talking about exponential order though. What we're talking about is a bound on the error, and what I want you to take from this is that for local truncation error, an upper bound is related to h squared. Now that's local truncation error, but we have accumulated error because we keep forming iterative steps. The total error in approximating y sub n plus 1 contains local truncation errors at every step, and we end up with global truncation error, and it can be shown that global truncation error using Euler's method is big O h. That means it depends on h. Back to what we saw when we first saw Euler's method, remember when h was cut in half, the step size was cut in half, the error was cut approximately by 1/2. It wasn't exactly equal to a half. A 16% error was cut down to a 9% error, but error is big O h, and I'm giving you that so that we can contrast it with something we're going to see in the current lesson. The current lesson is going to show us an improved Euler's method, which uses an average of two slopes and has a local truncation error of big O h cubed. We don't really focus so much on that in our work. The global truncation error is big O h squared. Now for a comparison, using Euler's method, the error is big O h. Using an improved Euler's method that we'll see in a moment, its global truncation error is big O h squared. Since h is small, think a tenth, a hundredth, a thousandth, h squared is much smaller than h, and so we have a much improved estimate. Now for Euler's improved method, but actually let's back up. The problems that we're solving here are of the form y prime is equal to f of xy. Remember that f of xy gives us a slope because that's what y prime is, at a point x naught, y naught. The improved Euler's method says, okay, generate a y sub n plus 1 star using Euler's method. Set that aside. Then we're going to find y sub n plus 1, and it is y sub n plus step size h times the f x sub n y sub n that we used in Euler's method, plus the same f, but now evaluated at x sub n plus 1, y sub n plus 1 star, all that divided by 2. This is the average of the two slopes that I referenced earlier. Finding y sub n plus 1 star is called a predictor step, and then using that number when we find the average of the two slopes is called a corrector step. And then this is a predictor-corrector method because it uses the two-step process. I think it would be good to see a couple of visuals here. The first one that I have here on the left was from a previous lesson here, very early on in the course. And it's what I showed you just a few minutes ago. We have a point x naught, y naught on the solution curve. And then we use Euler's formula to get, or Euler's method to get x1, y1, a point on the tangent line. This new method here, so now in the current lesson, says, okay, do that same thing, but the output that you get, we're going to call it y sub 1 star. Then using x sub 1, y sub 1 star, we get a slope of a pseudo-tangent line at that point. And instead of using either the original slope of the tangent or the slope of the new pseudo-tangent, we find an average of those two slopes. Using that average, we get like a pseudo-tangent line, and then a point on that pseudo tangent line becomes our y1 approximation. And as this visual indicates, the approximation for y1 is better than y1 star, which we got using Euler's method. We'll see what using this method actually looks like in the next video.